And the difference is, for those of you who may not know, typically we'd have to dissolve a solid material in order to introduce it into an ICP. With laser ablation, we sample the solid directly, where we create these very, very small submicron sized particles and then introduce them into an ICP plasma, where they can become ionized and analyzed by mass spectrometer. So we have a high energy laser focused onto a sample surface, producing very, very small particles, and then those particles can be scavenged by a flow of gas and then introduced into the ICP for analysis. It's very important that we consider how much sample we are removing. In the case of laser ablation, the standard method that has been reported by Night Crime requires drilling a hole that is about 90 to 100 microns deep and about 50 microns in diameter, approximately. This translates to about 300 nanograms of material. And there have been some reports, some papers that suggest that you need at least 30 by 30 by 30 micron cube of glass in order to characterize it well, in order to get a homogeneous sample. Even so, removing this very small amount of material, we get very good detection limits, so sub-part per million. This allows us to do very good analysis of this material. So we have done some work in our lab looking at very small fragments. People often ask, well, how small a fragment can you analyze? So this is less than 1 millimeter by 1 millimeter wide and long. The problem is you want to be able to characterize an entire windshield, for example, or an entire bottle. And we'll hear from Karen a little bit later about laser ablation on containers. So you need to sample enough in order to characterize that material. That's very important. So we have some publications related to that. We also noticed that depending on the sample size, so here one of my former students sampled different sizes of, say, this NIST standard 610, and we get very similar results even for very small sizes. And this is just distribution of different elements or ratios, looking at the expected value in red and what we see for the different sizes. They're very, very similar. So this method turns out to work very well. And so we want to see how does it perform when you're trying to discriminate between very similar samples of glass. For example, windshields in cars or side windows of cars. So I asked one of my students to go out and collect glass from 14 different vehicles. These are cars that were manufactured between 1995 and 2005. And she collected 41 different glass samples from 14 different vehicles. And I asked her to analyze them by this method. And for those 41 samples, you can create 820 possible pairs. And when you combine all of the elements, you get 8 pairs that are not distinguished. You can tell them all apart except for 8. That's 1%. So 99% discrimination is very good. But then I asked her, well, what are those 8 pairs? And she produced this chart showing that the outside and the inside windshields of these vehicles, these are glass that are made in the same plant around the same time, have indistinguishable elemental composition. So for the 8 pairs, it turns out we have some explanation of why we can't distinguish between them. The reason why this works so well is that the analytical technique is very sensitive and very precise. And if you look at, say, a different set of 21 glasses, you can see that there's enough difference just in the strontium. So when we combine 14 different elements, we can discriminate very, very well. Okay, so here's the precision of the measurement or the distribution of the strontium in a glass sample versus the distribution in all these glass samples. So that's why this method works in discriminating different glass samples. Here's the typical limit of detection. Here's the typical concentration range of these elements in glass. And this particular element menu is selected because we find that it is discriminating. The title of my of my presentation includes scanning electron microscope EDS as an elemental technique, and many people use it. One problem with SEM EDS as an elemental technique is that it has not as good a detection limit as laser ablation ICP-MS. So 1,000 parts per million, approximately 0.1%. Below that, you cannot see it. So in this case, iron at these operating conditions anyway is very difficult to see. We don't see very good peak of iron. And though that element list that I mentioned is very discriminating, doesn't show up on the list of elements that you can detect by SEM. The second problem with SEM is that it's considered more of a surface technique. So we can sample very small depth into the sample. So remember I said you need at least a 30 by 30 by 30 cube in order to characterize a sample of glass well. So the people who are doing SEM EDS really need to sample in different locations, many different locations, in order to average the concentration across many samples. XRF is a better technique in terms of sensitivity. The typical sensitivity for XRF, depending on the element, is about 100 parts per million. So an order of magnitude better. So here we will see an iron peak, and we will see strontium and zirconium. So people who do this routinely get some very good results. The other advantage that XRF has is the penetration depth of the sample for something like glass is into the hundreds of microns, maybe even a millimeter at this operating condition. So we're now taking bulk analysis. We are satisfying that 30 by 30 by 30 cube requirement for sampling depth. So this turns out to be a very good bulk analysis technique. When I sent those 41 samples in a blind test to my colleague Scott Ryland at FDLE in Orlando, I asked him to analyze them and let me know which of those he could not distinguish. Well, he came up with the same exact 8 pairs. He had 99% discrimination, and after his analysis, he came up with the same pairs. If we were to plot his data, this is XRF intensity with the laser ablation ICP-MS quantitative analysis, you get a very nice linear correlation. Okay? So XRF works very well in the hands of somebody who's doing it very well. The other topic I want to cover really quickly is LIBS, and it's been around for a long time, almost as long as lasers have been around. And what you do is you take a focused laser beam of very short duration, nanoseconds, onto a material surface, creating this plasma. It's totally ionized gas. That has a very high energy, and that plasma has the ability to excite the substrates, atoms, and ions. The characteristic emission that comes out of that plasma can then be resolved with a spectrometer to create a spectra. You can sample gases, liquids, and solids, and with the advent of less expensive lasers and more stable lasers and better and cheaper spectrometers, you've seen really a resurgence of work in this area. So there's a lot of research going on, but it is still not as mature as an analytical technique as ICP or XRF. The advantages is that you can detect all the elements simultaneously. It's very fast, it's very easy, no sample preparation or very little. It's almost non-destructive, and it has what I would say good sensitivity for a wide range of elements. And it has the capability of doing this remotely. Now we can start thinking about field analysis and even remote analysis. There are people who are doing LIBS at 100 meters away using a laser beam focused 100 meters away and a telescope to look at the plasma that's created. The difference between an ICP and a LIBS plasma is that the ICP is centimeters long and wide, and a LIBS plasma is only millimeters long. The ICP has a sustained plasma, while the LIBS plasma is short-lived. It only lasts in the order of microseconds. The energy density, or the electron density, in the plasma is very similar. So we have a lot of energy here to be able to excite whatever's in the area of that plasma. So it's very high temperature for a very short period of time. So here's what happens. You take your focused laser beam onto the target surface. You create this plasma that lasts microseconds. The material here interacts with the photons to create ionized material, free electrons, which those free electrons can then interact with the material again for the duration of the time that there's energy there, which is microseconds. So here's a time scale. This is taken from Russo. In the femtosecond time frame, there's only enough time for electrons to absorb energy. In the picosecond time frame, electrons are liberated from the surface. And in the nanosecond to microsecond time frame, we create this plasma. If you put a spectrometer right here, you can view the emission, which is characteristic of whatever the material is. The laser ablation experiment scavenges these particles and introduces them into the ICP. Okay, so that's a different experiment than the LIBS experiment. So we have a nanosecond pulse plasma, or nanosecond pulse laser, that lasts about 10 nanoseconds. We have the creation of ions and neutrals. And what we need to do is wait a little while before we turn on our detector. Otherwise, we get Bernstrom, and you get white light. And you get line broadening and a very high background. You have a lot of signal, say 1 × 10⁵, but they're very broad, and there's not very good resolution. If you wait 7 microseconds in this experiment from Kremers, you get much sharper lines, and you see here the calcium lines, and you see the aluminum lines that you cannot see here. So this is 2 very important times. This is the delay between the laser pulse and the time you turn on the spectrometer, and this is the time you observe the plasma for. So you can control those times in the typical LIBS experiment. You have a laser beam hitting the sample, creating, this is what we're interested in, this radiation, this light. The setup that you need is very simply a laser, the ability to focus the beam onto a sample surface, and the ability to collect the light into a spectrometer. In this case, we have an intensified CCD camera, and then you need that delay generator to control the timings for the laser pulse and when you turn on the spectrometer. If you want to get really fancy, you add a second laser, and you come around the side, and a couple of microseconds after you create that initial pulse, you reheat the plasma. That seems to enhance the technique. The sensitivity of the technique goes up, so there's a lot of advantages of doing this. This is our setup at FIU. We have the laser bringing, and this is the optics that deliver the pulse to the sample area, and then this is the optics that actually collect the light into the spectrometer. This is a typical output of a spectra. The range here is from 220 nanometers to 950 nanometers. We have a very high resolution spectrometer, and we're using, in this case, 1064 nanometer laser. We're only doing 10 shots. If you focus in on the area of the strontium peaks, you can see that for a sample that has 500 parts per million, we have very good signal to noise for strontium peaks. We have been trying to use different wavelengths to see how that affects our ability to ablate material and then observe the plasma. So we're doing some of those experiments. Here's your typical NIST 1831 glass. Has a concentration of 90 parts per million approximately. You can see fair signal to noise. Using a different laser wavelength, you get very good signal to noise. So this actually translates to getting a lot of information. Using that double pulse experiment, we are seeing lines that we did not see with the single pulse experiment in this case, and we get enhancement in the intensity of the lines for the double pulse, as is reported in the literature. So you can plot a single pulse experiment in green in terms of intensity, the double pulse experiment in blue, so you get increased intensity. And then in red is the concentration as determined by laser ablation ICP-MS, the quantitative analysis. And you can see that it tracks very, very well. If you want to plot it this way, you can see that over a very large range, say 500, we get very good correlation between LIBS and the laser ablation as we do for XRF. The only problem is LIBS, for 10 shots, removes very little material. So we need to sample about 50 to 100 shots. So this is now something we're doing in order to get better characterization of the material. So we don't have to do multiple shots across the surface to approximate what the laser ablation experiment is doing. So there's lots of things that affect reproducibility in the LIBS experiment. Like I said, we need more than 50 shots. Laser stability is even more important than laser ablation. How we focus that laser beam onto the sample surface is also important. We want a very nice, tight, even focus. And then how we observe the plasma is also very important. How we observe the light coming is also very important. So we have a collaboration with colleagues at the University of Florida, Jim Weinfartner's group, and Igor Gornushkin there has developed this software to do correlation spectroscopy, where we can take glass samples that have been analyzed by LIBS and compare them to a library of other samples that have been analyzed. And it gives us what is the best correlation for this very rich, information-rich spectra. What seems to work is to mask some of the lines if they're too large. So if we remove the very large lines that don't give us additional information, that seems to work better. And those same 41 samples that we did by laser ablation and XRF, in this case, we have, if we use rank correlation, we get 99% discrimination. We have one type 2 error and 2 occasions where the data agrees with the laser ablation and the XRF. That is to say that these 2 were distinguished, or sorry, not distinguished, and 6 cases of type 1 errors. So we have false exclusions. So we still have some work to do with LIBS, and we are fine-tuning this methodology. And I thought I'd put up this slide comparing these methods. And you might disagree with some of this, but here we have sample penetration, hundreds of microns. LIBS is operator control. You want to get at least 30 microns deep. Laser ablation, the way the methods that have been published, we require more than 30 microns. Sensitivity, laser ablation, I would say, is the gold standard. Precision, I would say that laser ablation is excellent. Analysis time, one of the advantages of LIBS is that it's very fast. Complexity, another advantage of LIBS is it's very easy to use. One of the disadvantages of laser ablation is that you need very complex equipment and somebody who's able to run it properly. And of course, the cost of laser ablation instrument is very high. But in the end, laser ablation is excellent, where we have some question marks about LIBS. So you've made it as an analytical technique when you make the cover of Analytical Chemistry, and dual pulse LIBS did that. You've made it as a forensic technique when you make it on CSI, and there is a laser ablation unit here. There is no ICP anywhere, but there's laser ablation. I'd like to acknowledge the colleagues at the Night Crime Network. Some of them are here today. The UF and Scott Ryland at FTLE, who helped, who's also a collaborator on this project. The people at Miami-Dade Police and Center for Forensic Sciences for providing samples. And then, of course, NIJ for funding, NSF funding ICP in my lab. And my postdoc, who's been really very helpful with setting up the LIBS apparatus in my lab. And of course, all the current and former students in my group. And I'd like to thank you for your attention. One last thing, we have elemental analysis workshop coming up in Miami, December 10th. Anybody who's interested, let me know. Thank you very much.